Hi. Hi. Hello. Hello. Hi, Beppo. Hi, Joseph. Hi, Possum. Thank you for checking in, Weetabix. And thank you for checking in, Possum. And thank you for checking in, Gren. And hello, Gren. And hi, Frost. Hello. Hello. Hi, hi, hi. I'm infected with a strong enthusiasm for all things science and excitement. I am too. I am too. How could you tell? How'd you know that that's exactly what I was thinking? How is everyone? Happy Science Friday. We're almost, can you believe May is almost over? I'm sad. Like, I've been having a lot of fun with the with these Cancer Science Friday streams. I mean, I know we can do a different topic, but I just love talking about cancer, you guys. Cancer research is just so fun. How can I not like talking about it? I can I want to keep talking about it, but I should make sure it's special. If I talk about it every week, it's not special, you know. But I'm not gonna stop talking about it still, you know. I'm doing okay. I'm just cleaning up my desk. Oh, I just cleaned up my desk right before stream because I realized I had some empty coffee cups. And I was like, if you can't see me when I'm like, I am simply a live 2D model, but if I was a 3D model, you would see that I move my hands around a whole lot when I talk, and sometimes I have knocked over like things in my way on my desk. You can't hear it, but sometimes I'll go, oops, and that's just me. I knocked over something. I'm too I have a lot of hand gestures. I have too many hand gestures. I'm being held back by the fact that you can't see my hand gestures right at this moment. But right now, I am doing a lot of hand gesturing. Can you feel that? Can you feel it? Can you feel it? Can you feel this hand gesturing? Okay. My desk is a mess and I really should clean it up, but I'm too lazy. I usually give it like a day. Like, I'll clean up and then I won't clean up, and then, you know, I get the build up. But it's not too bad. Don't worry, guys. My desk is not that messy. I don't have it that messy. It sounds intense. It's very intense. I'm shaking you. You don't know it, but you are being shaken right now. Every bacteria bud happening, like, you are getting shaken. Shaken with excitement. We gesticulate. Is that the word? I guess that would make sense. Hand gesturing. You're my kitchen cleaning background, I say. Good job for cleaning your kitchen. I need to clean my kitchen too. I hate mopping. That's probably like my least favorite chore. It means you use hand gestures while I mean, I figured from the context clues, but yeah. That makes sense. Okay. Today, I think for today, I have a lot of notes written down. What's this digital twin business? We will get to that, Possum. That's actually the first topic. So what I wanted to talk about, we've talked a lot about different kinds of, what cancer biology is, some different cancer therapeutics. And now I kind of want to go into like the topic of like, what does it mean? What does it like mean to talk about different, I want to talk about where cancer research is going. I don't want to get too deep into therapeutics. I could have had a whole stream just talking about what the new therapeutics were and new like drugs and like all that, but it's easy, like that's not as fun, and it's also like super granular. I'll talk in like broader strokes. Professor Nico, I am Professor Nico right now. I am teaching. So in this case, I'll start with the digital twins because I think the digital twins are kind of the coolest thing. And also, I think that's just funny. Digital twins. Digital. They're digital twins. It's you, but digital. I gotta draw a computer. How do I draw a computer? And that's you. That's you. It's you digitally. So, digital twins don't really come from they originated from, I believe, aerospace. And like the aerospace field, funny enough. So NASA used to build digital twins. So they would be a real, like, there's the real spacecraft, and then they would do computational models of that spacecraft. And so instead of trying to figure out, like, you know, hurting and damaging their expensive spacecraft, they would do simulations with their digital twin of the spacecraft. And, you know, it kind of makes sense, right? You don't want to do things to, like, the actual guy. You should run models to make sure, like, hey, does it work? What do you know, like, should we, you know, is there something we need to avoid? Is there any obvious issues that come up when we do things on the digital twin? The digital twin makes me think of a simulated brain scan of myself. It's kind of, it's not exactly, it's not just a brain scan. My digital twin is just like me, for real. We're digital twinning. Digital twin? When your, like, immunologically not compatible friend says we're digital twins, then you like side-eye them. Hello, Dr. Z-Track. So, oncology research kind of reheated the aerospace nachos and said, what if we just did the digital twinning too? Like, what if we just use this idea of simulating? Oh, autoclave. And you got me. You got me. Thank you for the autoclave. So rather than having a patient go through so many different trials and tribulations on the different treatments they can get, like, imagine you just want to figure out, well, what will they respond to? So we create this profile called a digital twin. We integrate so many different aspects of a patient's profile. We take their genomic data, we take their metabolic activity, we take a lot of spatial architecture, like through spatial sequencing. It's a very expensive process. That's why this is, like, very future talk. This is very future cancer direction. Right now, this is not something your average Joe is going to be able to do. Like, to get all this very individualized data for your cancer, and then also having people run simulations, many different simulations on how your cancer might respond. It's probably not happening right now. Probably not happening, like, anytime soon. But we imagine, a lot of cancer researchers imagine, that this could get closer to standard of care, or at least maybe not standard of care just quite yet, but closer to being an approachable, feasible option for patients, especially with things that are difficult to do biopsies with. So, if you don't know, a biopsy, we gotta take a little piece of the tumor. We gotta pluck a little piece of it. And certain tumors and cancers, it's easier to take that little piece out. But if it's something like, let's say, glioblastoma, which is a brain cancer, it's not as easy to take that little piece out. You don't really want to keep taking the little pieces out to see how the person is responding. So we might see this more frequently in the coming years when it comes to cancers like that. What's the alternative for an average Joe? I think the average Joe right now will still be, for a while, until this becomes more commonplace, you're probably still going to have to get a traditional biopsy, and then they sequence it, and then they will have to find, hopefully, the best match for you. And unfortunately, depending on the type of cancer, you might have to go through some toxic side effects or things that just straight up don't work. And that's a little sad, but, you know, with there's technology to make it so the choices we make on, like, investigational therapeutics that the patient goes through is better. It's sounds obvious when phrased like this, but the more people are involved with creating processing, the more the price of it tends to hike. Yeah. It's right now, like, digital twins really require a lot of effort. But, you know, I think it's going to... We'll see it more. There's a lot of initiatives right now to get this to become something more approachable. I want to say affordable, but it's probably more like approachable. And this is, like, federally funded projects too, and they involve a lot of, like, mathematicians and oncologists and computational biologists, and yeah, like I said, it's, like you said, it's a lot of different... It's a very interdisciplinary, so that means... as in there's many different fields of science involved, and so it's gonna be expensive. It's gonna be expensive until we see a way to make it easier to map out someone's specific tumor into a digital program. Quick question, what is digital spacing? Digital spacing? I don't know exactly what digital spacing means. I almost heard math magicians. They are kind of like math magicians. And, like, I don't know math that well. I don't know math very goodly, so, you know, they kind of do magic. Simplified, or you input many information, output many information we use to guide treatments. Yes, that's a great way to break it down, Joseph. I wonder what's a lower price basement, twinning or CAR Ts? I think twinning. Oh, that's a hard one. I'm kind of curious, but I also, like, I was trying to look up prices for not CAR Ts, but digital twins, and it's like one of those things that I feel like I couldn't really see anything. I saw the figure of $50K per trial participant, so it's pretty high up there, but I don't know where that number came from. Like, $50K per person, that's a lot of money to, like, make their digital twin. It's an expensive twin. That's an expensive twin, you guys. So, if you ever have a digital twin, I hope you don't, because that might mean something's wrong. But if you do, you should appreciate your twin, because it's an expensive twin. How far in the future is this digital twin gonna be? I think we might see things in the decade or next decade or so. Like, I think a lot of new programs and, like, algorithms and artificial intelligence is helping, actually, with creating these applications, mostly because there's so much data that needs to be integrated to create a digital twin. Like, and the data they don't really speak the same kind of language, so to say. There's, like, histology imaging files, which means, like, it's like literal pictures of the tumor, and that's not words, that's just pictures. Then there's genomic sequencing, which is just a bunch of, like, letters and base pairs. That's also difficult for a person to interpret, like, easily. Then there's EHR records, which are electronic health records, which just shows the patient's whole health history, which might be easy to interpret for a person because that's the most close to words. But you have to consider that you have to do that for every single patient that goes along with this option of finding a treatment. And that's a lot. That's a lot to go through. It's a lot to go through. How many red super chats to twin? We gotta maybe we can create a fun GoFundMe for my digital twin, my own digital twin. Could I hang out with my twin? I think the twin might not want to hang out. The twin might be busy going through its own kind of digital hell, because it's going through, like, hundreds and thousands of different simulations of getting treated. Maybe the twin might not want to do anything. The twin might, like, just want to chill because it's getting, like, blasted with cancer therapies. So, digital twins, Very cool, very cool, very cool idea. It's probably my favorite, like, future-y kind of cancer therapy. Mostly because it sounds cool, and also I think it would solve a lot of the issues we currently have with cancer therapeutics. It is very, very hard right now. One of the biggest, like, challenges is when someone has a cancer mutation and, you know, they can't... We don't have a standard of care, or there's no, like, traditional method to treat their cancer. And so we gotta put them into the world of, like, clinical trial testing. And there's so many different options, and you don't want to mess up. You don't want to put them somewhere that they might not respond, because it's such a big burden. Sometimes people have to, like, go all over the, like, they have to move, or it's, like, far away. It takes a lot out of them. They could have adverse side effects, blah, blah, blah. It's a lot. So this would be a really good method, but we just need it to be a little more affordable. So, what else is new? I'm looking through my notes. I wrote a lot of notes. Oh, this one's kind of cool. It kind of goes along with digital twins. It's kind of the reason why digital twins are, like, still in this investigational aspect, because we kind of need this part to also become more affordable. But it's a spatial transcript tomics, which is a heavy mouthful. The basics of this is spatial transcriptomics is it tells you where in a tissue a cell lives and who that cell's neighbors are. It gives you a lot of information about a cancer cell or cancer tissue when we pluck it out of the person. When we pluck out this is their handy tumor, and we pluck out a little piece of it. We just say, yoink, we gotta check out what's in that guy. And then we can learn it's made up of all these little guys. Ding, 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 ding. And all that information is useful. Every single dot there, that's a useful dot. And we want to preserve that information. A lot of times when the old method of sequencing, you don't get to preserve this information. You don't get to preserve that this guy is next to this guy. Instead, usually you will just know this guy exists and this guy exists, but you wouldn't know, oh, they're neighbors. And that information could be useful because you're like, well, if they're neighbors, are they talking to each other? Are they doing something? If each one is getting simulation to treatment, how can I assure the VOD since it might not be able to account for real world factors? Well, that's why it's very expensive, because it tries to get as close as it can to being you. Like, it has as much information as it can get, probably as close of enough information as it can get compared to a doctor. Like, it's gonna have as close to, like, your whole real life, like, experiences and your biological experiences and your medical history and all your tumor information. There's nothing, like, closer than it can be than that. But there's still, like, of course, issues, and that's why it's expensive, because all these computational biologists have to account for all the little issues. It seems hard for me to imagine how our genomic data can be parsed into useful... I got autoclaved! Right in the middle of my... blah, blah, blah. Hey, thank you, Gren. You got me. Okay, it seems hard for me to imagine how our genomic data can be parsed into a useful format for simulations. It's very difficult. This is some of the most, like, cutting-edge research. And I think a lot, like, I have a really hard time understanding it myself, as I am not a computational biologist. Those people, they're doing some crazy, like, math and science, like, integration and programming. It's a lot. It's very, very tricky stuff. I've listened to them talk and present a lot of work, and it's a lot. How common are cell owners associations? What do you mean exactly by cell owners associations? Like, as in, like, how, like, yeah, could you explain what you meant? It's relevant to studying how some cancers metastasize and spread to their neighbors. Yeah, it does give us kind of like some information of like how maybe certain cells have different hallmarks of cancer, like the metastasis, like angiogenesis, things that make it spread. It can kind of give information, insight into that. A bit scary to think about an EME existing entirely in a digital space. Well, you would hope doctors would never do anything harmful. It is scary though. I can see why some people might be apprehensive about enrolling in something like a digital twin program, because they might think, I don't like the idea of like a whole me being in the world in that I can't control. The autoclaves are on fire today. You guys keep getting me. And thank you for the check-in, Nooblet. What is an autoclave? An autoclave is that's what you were seeing me get put into. It's where they sterilize me by throwing me into a bunch of hot heat and pressurizing me and trying to get rid of me. It's basically to kill me. And they keep killing me, but I come back. It's what in real life, it's what you throw tools in science in to sterilize them. Like before, let's say a doctor is gonna like open you up, they have to throw their tools into an autoclave so they make sure there's no bacteria entering you. So, where was I? Is it spatial transcriptomics? Oh, right. Spatial transcriptomics. Right now, the standard of transcriptomic, like of sequencing, is you get some tissue, you grind up that tissue, and then you only get like individual cells, and you lose a lot of data. You lose a lot of data on different types of cells, different gene expressions. You learn, and or not, you keep that data, but it's like you lose that spatial information. And sometimes you can also miss some data because things can be buried and very hard to like dissociate tissue, you know? And that is its own problem as well. This feels a bit over my head, but interesting. It almost sounds like using a virtual machine for computers and cloning the machine. I guess it's kind of similar to it in that way. There's just a lot more, yes, but like in a biological sense. Like you're cloning, like you're almost like taking the whole human, but not really. Because there's still a lot of aspects that we just don't really know about. And that's why there's problems with the digital twin, and there's still a lot of work to be done, because the fact is sometimes we get surprised at how people's immune system responds. Imagine digital twin treatment for psychotherapy. Sounds like a nightmare. That one might be more difficult. There's at least aspects of like, for cancer treatment, you know, a disease is like, something like cancer is a little bit easier to, I think, handle because of the way like we understand signaling pathways, and that's how cancer kind of proliferates. I'm no psychotherapy expert though, so someone could like probably say something more about that than me. Very rigorous dataset made of many tiny profiles of a person, from nutrition, physical activity, health variance, not even scratching the surface. Exactly. It's as close as it can be to you, but still not quite you. We'll see how that turns in the future, but you know, right now it has, I think in clinical trials, it's been doing good headway in improving the success rate of how a patient, like choosing the right clinical trial for a patient. It's not, I don't think it's like a huge like increase in the success rate just yet. But I mean, it's still, the digital twins are still pretty immature, and there's not like enough people subscribing to it. Well, thank you for the follows, you guys. We will like, I'm sure we'll see how that develops in the future when people aren't having to drop 50K on it. If I pinpoint the location of my cells and its neighbors? Can I buy property on my cells? No, I don't think you can buy property of your cells. The cells don't subscribe to the capitalist nature that you can buy property. Like property, the cells don't, they live their life freely from like this idea of buying property. So, spatial transcriptomics gives a lot more information. This is not so crazy right now. I don't think we don't see it this is not like something that you'll really see as much in like the patient facing sphere. This is like really more in the background. Like a lot of commercial, like big pharma commercials are already using this kind of to understand people's like tumors and then go from there to help create like new cancer therapies or understand why certain tumors act the way they do. They get information on like the tumor microenvironment, like understanding where the immune cells are, how they're responding, how are they infiltrating. It's like a geography. Yeah, for now. Where do digital twins and spatial transcriptomics lead us? So for like digital twins will definitely lead us to more of helping people find the treatments that they are more likely to respond to, rather than going, you want to try this one and you don't respond. People are like on a time limit when they are in these situations. They kind of need to find something fast, and you don't also want them to do things that like are a waste of time. For spatial transcriptomics, this is definitely more in the drug target discovery like field. That's where we're seeing it the most. We're being able to like you map out where the genes are with the tissue and their locations, and then you can kind of understand better, well, what's a good target? What if we like attack this guy right here? Like, what if that's the key to making sure this tumor doesn't grow anymore? That kind of stuff. I think this is basically becoming the future of like how drugs are getting developed, like how researchers are understanding where we want to target therapeutics. If I pay taxes, doesn't that technically mean my cells also pay taxes too? You know, very good philosophical question. If that are the cells you? Let's see. I don't think there's too much else I can say about spatial transcriptomics. What I keep in mind is cancers are different. Cancers are very different, and that's one of the reasons why this is such important information. Everyone's cancer is so different, and if we can get more information on like why they're different and like what are they, what's going on, who's talking to who, it's just, it helps a lot. It helps a lot. It's the future is basically in all, and this data, when you do spatial transcriptomics and with single cell sequencing, aka like you're looking at like individual cells, like every single cell in that tissue you just like process, you're looking at every single teeny tiny cell and all its neighbors and friends, and then they're positioned in certain ways. That data is very difficult to read. I wonder if I can find like a good example of it. Single cell RNA data. I'm just gonna copy and paste a random one. Ah, it's too big. Okay, so this is like an example of the data that you get from this. Every single little dot you're seeing is like is a cell, and they cluster together, and they're giving you information basically on who's its neighbor, and then you kind of create patterns of like, this is group number 1, that's group number 2, that's group number 3. It's by colors. It's so difficult to read this data. Like I had to do this for my grad school project. I would take fat tissue and we would like crush it up and then get all this sequence the cell data, and we would want to understand exactly what's happening and like what's in this old fat tissue versus the young fat tissue, young fat tissue, and then you'd compare the two, and then you'd kind of like look for the differences. It's something I think best left to like some computational programs. Like I feel like as a human, and I would talk about this with my PI, like I feel like I would show my data to like a bunch of different people and they would all find different patterns, and I feel like it was so difficult to actually have a standard. You are the cells you made along the way, or maybe the cells like are the friends we made along the way. You know, like if I those are some good questions and comments. I agree. I imagine there are different cell countries and factions. They kind of are. That's like the way you should think about it. Like it's like you would say usually like, I don't know exactly on this data. I just stole this data. Sorry to the people who own this data. This blue one, they're supposed to be like the closest to each other. Like they have something linking them together. And then this one is its own linking. This is its own, and that's its own. It's not. It's very cool, but again, I think this is so hard. I think there's a lot of like AI, like people, I've seen a lot of like people creating AI models that they don't understand how they like determine the patterns, but then they do. I don't know how those work. I'm curious how that helps with the like reading, and I wonder how like accurate it is, and like what's the consequences of like just throwing your data into an AI program to like find the patterns. I'm sure it's not like terrible because AI is kind of like weird with like pattern recognition in a way that humans aren't good at. Yeah, it's just kind of like a k-means cluster, but you have to remember like every single one is a cell. Is the data usually isolated, or are there any combined variables? As in, like, are there times when, like this section might be green? Like, is it more... I think you can kind of manipulate the data as you need. It's been a while since I've done this. So mine's never looked this good, mind you. I feel like mine's looked very, very messy. I wish I had some of my old data to show. But they were, like, there would be, like... islands like this, and then inside there's another island like this, and I couldn't understand what the data was saying. Now that you mentioned fat tissue, I wish we had talked more about the relationship between cancer and the fats in our body. Do they feed the cancer, or do they starve it by redirecting nutrients to them? Oh, that's a fascinating topic. It's a complicated, there's a lot of facets to that. I would love to talk more. I can talk more about that in our Discord, Possum. Mostly because I might ramble on and on and on and on and on and on about that. And there's a lot of different aspects to it. It is fascinating, though. I should have talked more about fat, considering I did whole research on the fat. Blah, blah, blah. Though, I guess my research, when I did fat research, I didn't, know too much about how fat, affected cancer. But that was something one of the people in my committee, they wanted to know about how this would work in, the model of cancer. And then I was like, oh my gosh. This is why you have to pick your committee very carefully in grad school. So the people, they always want to insert their own research into it. Would be interesting if that research showed us that the potential fungal relation to cancer is linked to fat cell consumption. That would be fascinating. What else do I have in my notes right now? Oh, this is a good one. This has to do with, this is a very broad topic. Detection. So one of the things that is like making a lot of headway right now, unsurprisingly, is improving our methods of detecting cancer, which is not, I mean, is it surprising? We're getting really good at treating them. And then we find that sometimes a big problem is we don't catch these things early enough. Because if we don't catch it, a lot of cancers, if we don't catch it early enough, we sometimes just can't do anything. Like, it's way past, we're past the point. Things are metastasizing, things are having problems. And that's not good. That's not good for anyone. We're learning about some cells. We are learning about some cells. We're learning about cancer cells specifically. Unrelated, but I'm vibing hard with today's playlist. I'm glad you like it. I think this is just a Maple Story lo-fi version 2 hours. You know how hard it was? I was looking for a longer playlist, and so many of these playlists are just AI music, and like I couldn't find like anything that wasn't an AI music playlist. This one I had to look for a super old one. Metastasize means spreading, right? Yes, it does. It means spreading from like where it originally came from. Now it's like invading other tissues. So, I learned that from Dr. House. Thank you, Dr. House. So what a lot of researchers has been focusing on are how can we make sure we find that people have the cancer early enough. It's a hard balancing game. Because there's a lot of research on the fact like you don't want people to go in and get tested too frequently because it ends up causing more problems. And then you don't want people to go too late because then they don't actually get tested. They don't get detected fast enough. So what can we do? So the whole point is we want to try to find ways that are methods of detection that are a bit more minimal, rather than having to like do some very crazy testing, like let's say put them through MRIs, like X-ray scan them, take pieces of their tissue. Those are very like hard, invasive, take a long time to schedule. We are trying to do things that are more like, what if we like look at their blood, like we take, do a simple blood test and we can like see if there's anything like DNA, is there in their blood. We take a little bit of their blood. Sorry, little guy. And we take that blood and then we go, is there any DNA, that shows, I'm like blocking that. Are there any like tumor DNA there? Is there any DNA of the tumor that we can detect? This is like the future. It's called circulating ctDNA. Circulating tumor DNA. This is a really cool tool, like new detection tool. It's not that new, but it's getting a lot more like attention nowadays. It's a really cool way of like finding out people have the, oh my gosh, you might have something, and it's not very invasive because it's just in the blood. Because what AI learns isn't exactly what that's because what AI learns is exactly what we want it to. It's like a horse that can do math. The reason it can do math is because it can read the microexpression of the person asking instead of doing arithmetic to get the answer. We can train an AI to provide the results we want initially. Small changes are small if it can make the AI act in ways we don't want because it learned the wrong ways. At least that's what I'm studying for, AI is complicated. AI is very complicated. That sounds handy dandy. Yeah, it's very handy dandy. This is already something we're seeing in clinical use, and the use cases it's just becoming more and more common. The important part is we need to like be able to create more ways for the doctor to detect the right kind of tumor DNA. So that's why we have things called CDX. Those are companion diagnostics. It's basically like, think of it as a little cheat sheet for the doctor to look at and go, okay, we need to make sure we're looking for these exact things. And those exact things, those markers, those are the things that will tell us this person might have a cancer of some kind. So you can see how like better understanding of what the biomarkers of cancer, and this all kind of like, if you can tell, like it all kind of ties together. The more we understand like the more we understand of this, like let's say we understand more of who are the neighbors of non-small cell lung cancer? Who are the things, what's happening in colorectal cancer? What's happening in breast cancer? What's happening in ovarian cancer? The more we understand of that, the more we get to like create a more robust detection method here. And that thing's not fully true. You can kind of teach AI to do the equivalent of mimicking your actions using calculator leading into a precise and correct. Yeah. I am no AI expert, so I can't say too much. But AI is complicated. You say lots of smart stuff? Thank you. I don't say that much. It's not like crazy smart. I am just saying what I've learned. I am just saying the things I've learned. Anyone can learn it. That's why I'm teaching you guys. You guys can pick up on this. And if you guys have questions, if you can't, then you can just ask me questions. And if you don't want to ask me questions, that's okay too. I'll just nod my head over here and keep yapping. You guys can follow along. Even if it's like 1%. My ADHD is on overdrive, so I'm gonna go. Bye, Gren. Have a good time. How do we detect cancer today? Oh, there's a lot of methods of how we detect cancer today. There's, you know, we can detect right now through this. We have a lot of different screening methods. There's things like mammograms, there's colonoscopies, there's pap tests, different CT scans. There's just a lot of different methods. But the problem is usually in order to do those screening methods, you kind of have to have these specific risk factors involved. And that involves, let's say you have to be, for colorectal cancer, you get it detected through something called a colonoscopy, and usually you can only start getting that detected at 45. At least that's in America. So if you're not 45, you won't get any kind of detection for colorectal cancer. But this is where the issue of we need to have better methods that are not so strict like a colonoscopy, because we are having a problem in young people globally where there's a rising incidence of colorectal cancer in people younger than 45. So before they can even get a colonoscopy, they are getting colorectal cancer. How do we stop that? How do we prevent? What can we do? It's not good. That's not good. That can't be happening. It might be because we spend so much time sitting down. There's a lot of different factors. Oh, thank you for the follow, Stellar. There's a lot of different factors why we might be having colorectal cancer incidence rise when we're young. There's people who speculate it has to do with the fact we sit so much. People speculate it's our diet. We don't eat enough fibrous veggies. Our fiber content is way low, and it's also sometimes people think about ultra processed food. If we're eating too many certain fast foods and oily foods and high sugary foods, it's not good for us. No one really knows why, but it's good to, what we need to do is have earlier detection methods to prevent it. And you don't know what I'm talking about, but I'm interested. I'm happy. If you don't understand what I'm talking about, I'm happy to explain any parts you don't get. A lot of research based off of very simple logic is super novel and difficult to do, simply because being the first to suggest a hypothesis scare requires you to question things a lot. True. Less than 90% of Americans get the fiber they should. I don't know the exact percentages off the top of my head, but I think it's a lot of people do not get the recommended fiber intake. So eat your veggies, you guys. You guys, I'm staring right at you. If you don't eat your veggies, I'm gonna get really sad. Don't get colorectal cancer. I don't want you to get colorectal cancer. Make sure you stand up. Make sure you eat your Fiber 1 bars, and make sure you eat your greens. Could you technically help me with my chemistry homework? Oh, buddy, I I don't know about chemistry homework. I'm pretty bad with chemistry. I'm pretty bad with chemistry, but I'm gonna believe that you can do it. Eating veggies, beans are good. Beans are very good. Beans are very good. Nico Fiber sponsor when? I know. Can I get a Facilium Husk sponsorship? I feel like every time I try to mention fiber consumption. Can I be the VTuber that talks about how important Facilium Husk fiber like supplements can be if you don't eat enough veggies? I tried the veggies in the supermarket. Tasted like chemical. Oh, that's not good. If your veggies taste like chemicals, there's always other ways to get fiber. Like, you could look into certain supplements. But, you know, yeah, you could look into certain supplements. I'll be honest, like, I think my favorite ways to get fiber are probably, like, the more... it's bad. I should be eating more veggies, but I do get a lot of my fiber through, like, the super heavy, like, the processed foods. Like, I eat those fiber wraps that are, like, 90% of your daily fiber intake. They're so good. Like, I can just eat one wrap and I'm done with my fiber intake. That's pretty good. That's pretty efficient. Fiber wraps? Hold on. I gotta show you guys the Giga Fiber wraps. Where are they? Mission. Where's the specific... Where's my specific Giga Fiber one? Head pat, thank you, Stellar. Look at the fiber in this tortilla. I usually eat these and I'm good for the day. Hello, Gauchi. Gauchi. Let me know if I mispronounced that. I worked at a Walmart before the pandemic. They had me spray food-grade wax on fruit to make it look better. I didn't trust the fruit anymore. And that is why you should wash your fruit. Wash your fruit. Skipping the answer is a great way to... Yeah. Chemistry is hard. Chemistry is hard. Are you sure it's not chemically processed food? Listen, every food is, like, chemically processed in some way. You gotta, like... I'm not, like, I don't really believe that much in, like, chemical, like, the words... When you start adding the word chemical, process, like, it's like everything's kind of been processed in something. I walked in on the whole tortilla debate. It's a good tortilla. 28 grams of fiber and 110 calories. Anyway, if you are like me and forget to eat your veggies or, like, don't buy a lot of veggies because it's hard to buy veggies for a single family household, I recommend, like, looking for ways like this. Get your fiber one way or another. I like the taste of funny chemicals. Me too. The funny chemicals make some tasty foods, like my GMO processed bananas. My banana has chemicals in it. I was, like, reading all about the bananas. Like, the bananas we have nowadays are not the bananas there used to be. I didn't know that. GMO, genetically modified organism. My mind was blanking on what the O meant. It means the farmers and the engineers did some funny things to make it taste a specific way and grow a specific way. I'm too European for the whole chemically processed foods thing. That's true. When I was in Paris, I will say the food tasted very, very good. It tasted very different. I love freezing veggies and kind of tossing them into things they don't belong. That is, like, the best way to go about it. I got lost in the fiber debate. Like every time fiber gets brought up, I have gotten sidetracked. I just plead to my audience every single time to like please eat fiber. Is there a downside on dry freezed food? No, I don't think so. Oh, thank you for the follow, Slushy. In Germany, I only see fair trade and bio or the GMO thing might be too American for some of you guys, but we do be doing a lot of food processing in some way. And like not all of it. I mean, it sounds scarier than it is. There's a lot of good that comes from doing GMO. All the European people are like, I don't know what a GMO is. I'm not familiar with European food regulations when it comes to GMO. Can GMOs give me a seedless watermelon? They do. Could you benefit to having a clipboard with a list of topics you want to talk about and check them off as you go through the stream? I have a list of the topics, but I just get sidetracked. But it's like fun to talk to the people, so it's I kind of like, it's nice to, I don't mind getting sidetracked. I don't mind getting sidetracked. I can always stop the conversation. Like right now, I can just go, okay, we're moving on to the next thing. Like that. I think the next thing I'm going to talk about is patient-derived organoids. There's an ad coming up, but I'm going to snooze it. So, patient... Why can't I draw? Oh, it's because it's on the wrong layer. Patient-derived organoids. So this is kind of close, like, it's kind of the more realistic approach that we can do when it comes to seeing how people's cancer will respond to... Oh, hydrate me, thank you. This is kind of the way we can look at how people respond to tumors in a lot more of an affordable way compared to just creating a digital twin. One question, what is it? Or what does organoid mean? So I was gonna get into that. An organoid is, think about it like this is our petri dish, and inside the petri dish is a little tissues. It's 3D tissues collected from a person who had from their tumor. So we basically grow their tumor and like mimic kind of like, you know, the structure, the complexity, the functions. We kind of mimic all of that in a stem cell in this petri dish. Is there a DC channel? Are you saying a Discord channel? There is a Discord channel if you want to go to that. Or a server. I mean, you can yap in there. So the 3D tissues, we can use that, and so we can play with it kind of just like how a cell is. We can figure out how does it respond to certain things. Does it cause problems when we treat this tumor in our petri dish with one thing? Or does it gain resistances? Does it do something? What's going on? And it's 3D, so this is like, it really has that structural architecture, the complexity of what a real tumor is like. Can humans build antibodies for cancers? Well, yeah, like that's a huge aspect. That's what we talked about a bit last week. There's a lot of therapies right now that kind of utilize the immune system to tackle cancer. It's not exactly antibodies. We create like certain we design certain antibodies to target certain cancers. Those are called monoclonal antibodies. But we also have ways like using T cells and B cells to fight the cancer. So we clone the cancers and study it. Yeah, it's kind of just like that. It's it's a little bit more complex considering the fact there's a lot of other aspects we have to keep in mind, and it's also specific to that patient. The fact that it's specific to that patient is a big part. There's a lot of push to go towards this organoid model. Like in American research science, there's like a huge push for institutions to do something like this rather than, let's say, like a mouse model, because we're having issues with mouse models really translating into our research. We don't really, sometimes the mouse model doesn't exactly translate very well. Like it might respond, but then in humans, it doesn't actually do anything, or it causes other problems. I talked about a little bit about this in my short above, like in the chat, why does it take so long to get new medicine? Mouse models just mouse is just not human. As simply as it can be put, it's just not a human. It can get close. We can kind of understand, like, oh, what problems is it causing? Like, oh, does it actually do something? Sometimes it can be close, and it's still like one of the best ways to test how safe a new treatment is before we start putting it in humans. Like, I don't know if you can even go directly from like cell to human clinical trial, like a phase 1 clinical trial test at this point. Someone can correct me if they know any better. There'd probably have to be some exceptional data. But I think in the future, we probably will see more of that as organoid, like patient-derived models start getting more and more popular. There's even the organoid models are even getting more complex. There's ones where you put like, I don't even know how to depict this. You put a whole chip in there, and that chip is like it can help mimic blood flow and mechanical forces and organ interactions, because, a tumor tissue is not just like sitting there in a dish. That's like it's not an accurate depiction of how it is in a human body. You want to also mimic like how it's moving, like it's getting, blood is flowing on it, it's like bumping with your body and all that can affect how a drug might respond. There's all these little factors that make it so hard to treat. Mouse variable makes different, yes. Yeah, it's just so hard. Every time I feel like even if you don't really understand all of these different issues and all these specificities, I just think the number one thing you should walk away with is understanding it's so difficult. Tumor is so complicated. It's not like one bad tissue. It's like very bad tissue that has so many different aspects to it. It's very multifaceted, and then you have to consider how it interacts in a human. And humans have so many different problems along with it. Everyone's different. Everyone's immune cell is different. Everyone's body is kind of different. We just are so different. And how do we keep that in mind? And these models are the way to go. Okay, well, let's see if this helps reconcile those differences or not. And even a huge problem is the fact that sometimes things get treated well. Let's say this model responds and you just don't it responds, but then there's a problems later down the line. That's something these organized models also help with. You can start seeing, like, is there any immediate problem like that happens? Does this person develop resistance afterwards? Is there a new mechanism that this tumor will take advantage of if we give it this treatment? Are organoids still part of the digital twin stuff? No, well, I understand why you would think they are similar, but they're kind of different. The organoid models are more in like the physical space. Like, these are like dishes of cells that people are working with hand in hand, versus digital twins, they are more in the like computational space. These are more like literal models, like numbers and programming and whatnot, whereas with the patient-derived organoids, people have to like do physical lab work. We kill every sick person. Oh, that's terrible to say. We should not do that. Just kill the cancer so easy, but the easiest way to do it kills the patient too. We don't want to kill the patient. We don't want to kill the sick people. We want to keep all. We don't want that. No hurt. Non-digital twins. Yes, it's not exactly a digital twin because it's not a like. It doesn't. This is a little less sophisticated than a digital twin in the most, but it's also right now the thing that's we're utilizing the most right now. It's less sophisticated because you can't tell it all about its like the person's previous medical history. You can't give it like real world data. You can't like give it responses right here. Also, we're in an ad break right now, so you know. I'll pause right here, but also, yeah, this is like, yeah. A lot of it does seem to like come back into how do we model people? Can the organoids be made with stem cells? Yeah, they can be made with stem cells. So are you a microbe? Yes, I am. It won't win any peace prizes, but it might be controversial. Actually, it'd be very controversial. We shouldn't talk like that. It's not very, like, it's not a very, like, good way to think. Do all microbes have pink hair? If they're gram-negative, maybe. That's just the kind of microbe that I am. I need to get my water. I don't know where I put it. I thought I left my water right near me, but I just only have my Sprite. What if we clone the whole person? Cloning the whole person might might be getting into like a more difficult territory, Josem. Like, what is a stem cell? The stem cell is think of it like the foundation of a cell. They're kind of like they don't have a direct role yet, and they can divide and renew themselves, and then they can turn, depending on the messages they get, they can turn into whatever specialized cell. So you can turn a stem cell into a muscle cell, blood, brain cell, depending on what info you give it. A beginner cell that just graduated high school and is ready to pick a career path. That's a great way to put it. If you clone a person, would it still be the same person? You sure are into philosophical questions, huh? The stem cell organoids are definitely used. Those are used in other types of research primarily. I think a lot of times with I guess I don't know too much how stem cells are utilized in the patient-derived organoid models. They probably are still utilized. Okay, hold on. I gotta find my water. Be right back. Okay, I found it. It was behind me. Oh, now I'm covering. Now I'm covering the stream. Oops. Oops. Let me move back down here. Are twins the same consciousness? I mean, it would be the same cells, but it would be the same consciousness. I think, you know, I don't think exactly it would be exactly the same. Probably because of how, like, you'd likely have different experiences that shape you. Like, from the point where you became cloned, like, you likely would have different life experiences. But this is, like, you know, very philosophical. Like, if you want to think more about that, you can go play something like Soma. I think that game explores that a lot. I got a question in cancer cells. Shoot away, Stellar. Tell me what your question is. And also, welcome back from the ad break. I don't think we have, like, too much more to go through. I'm looking through my notes as I look. I was thinking about Soma the whole time you were talking about this. I mean, I think I think that game is really fun. The story is, like, interesting in that regard. You can do some big philosophical think-thonking about what exactly it means to be you, and what it, like, and what, you know, consciousness means, and experiences shape you, blah, 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 all the philosophical aspects. Thinking for prolonged periods hurts my brain usually. I feel like my brain's kind of, like, always wired on. It doesn't feel like it ever shuts up or stops. Is it possible? It's just possible to cut off the cancer? Why, yes, it is just possible to cut off the cancer. That's, like, one of the first treatment options is usually seeing if you can just do surgery. Like, a lot of cancers, like common cancers, solid tumors, you just cut off the cancer. The problem is it's not always that simple and doesn't guarantee that you won't get it again in the future, because it could be somewhere else. There could be problems in your DNA, inside your genomic, like, DNA, that causes problems for you later, and you might develop something, and then you might have to go on a treatment and blah, and yeah. And then also certain cancers you can't just cut off because it's in your brain, or it's in your blood, or it's in your bone marrow. It's, like, in places you just can't do anything about, you know. And those are the nastiest of guys. What is a carcinoma? That's a cancer that originates in your skin tissue. So stuff like breast, lung, prostate, pancreas. Those are the most cancer ones. I'm looking at my final... I think the last one I want to talk about. Thank you, Possum, for trying to keep me on track. Thank you. I appreciate that. I think the coolest thing we're getting into nowadays is protein, folding programs. I think if you are, like, a bit into the science field, you might have seen stuff, like, regarding this. This is getting a lot of headway, especially because of AI. So in the 2024 Nobel Prize in Chemistry went to AlphaFold, which is a protein structure prediction program. So it helps... It kind of has created this cascade of AI-designed drugs. So I know that sounds like there's a lot of anti-AI pushback, but it's actually done a lot of useful progression when it comes to this cancer therapeutic field. It's because this like kind of like work takes so long, and it's really, really difficult. AI can really, really speed this up, and it's done a lot of good of figuring out. It goes from a protein to a predicted drug. it's automated, it's fast, and it's been able to identify a lot of protein targets implicated in cancer, and then figure out a structure, and then design a molecule or that can be used as a drug that can, prevent, like, stop that protein from doing its cancerous actions. This, like, usually would, like, in traditional work, this could take like a decade. This could take a decade of, like, a bunch of labs coming together trying to figure out how do we like do something with this protein? How do we, like, target it? How do we attack it? We saw that with, like, KRAS. KRAS is the drug that the oncogene protein that we were talking about in previous lessons, and it took over 40 years before we were able to see the first drug to, like, target it. And it costs a lot of money. That's a lot of money. It's not just time, it costs a lot of money. AI can compress this AI designed drug molecule pathways. They can compress this very, very goodly. It can make the structural biology a lot easier, can make testing and computational testing so much freer. It's incredible. It's honestly incredible. I think, like, it's going to be interesting seeing the future of so much, like, of the future of cancer research, because as you can tell with the digital twins, a lot of this is computational. The future is truly more online, like, when it comes to the cancer research. A lot of it's going to be modeling of some kind. It's going to be like simulations, because the reality is it's really hard to do these kind of research, like, in a wet lab, like, to be struggling over there and, like, pipetting and doing all that. That takes a lot of time. It's a lot of work. It's a lot of time. It's a lot of money. It sounds similar to people using computer models to create new knot settings, but instead of tying strings, the AI is turning proteins useful. Yeah, exactly. And there's other programs aside from just AlphaFold. AlphaFold is, like, the new hotness right now because it's, like, AI generated assisted. There's also something called folding at home, and also this is a cool one because anyone can do it. You can give the people that work on folding at home some of your computing power, and it helps try to generate different protein structures. And that's really cool. It's a very interesting. I recommend you can look into this yourself. Folding at home and AlphaFold, they sound like they do similar things, but they actually don't. I also, at first when I heard of AlphaFold, I was like, did they just take folding at home's nachos and then win a Nobel Prize in chemistry? But no, they said that. I've read folding at home's FAQ regarding this. They said that they use AlphaFold kind of as a jumping off point. It does a lot of generations of, like, different protein structures, and then folding at home can kind of figure out how dynamically that protein might look in biology, in, like, a physiological sense. Like, how does it fold up? How does it move? Because it's one thing to know exactly a protein structure, but you also, like, you have to remember they're 3D. There's a lot of aspects to them. I think that's why, it's a little off topic. I think that's why biology and human biology especially, it can be very difficult to understand, like, for us, and why things don't work the way we think they always work when we do tests. Because everything is, like, 3D. These are, like, real, like, we want to, like, picture them in our head. Like, when we think about a protein, they just kind of seem like a 2D thing on a piece of paper, especially because that's how we typically learn them. Like, it's on an exam in a textbook, and it's just this flat thing. But all these things are little dynamic creatures of 3D shapes, and, like, they bump and interact with stuff, and they can be dynamic. They move around. Crazy. Tools are tools. Just because a lot of capitalism leads to cruelty with those tools, that doesn't mean the tool can't be used for good. Exactly, it is true. The only time I've heard of protein folding is in prion disease. I don't think they could profit from my computing power, man. My BC can barely handle its own data. That's fine. I always recommend you guys can look it up, folding at home. It's very cool. Protein folding, it's cool that you know about prion disease. I love, the prion disease is such a cool topic. But, I'm trying to find a good picture of protein, like how they fold. Where is like a good picture of it, of protein structures? I'll just steal this one, I guess. I guess that one's fine. Where did it go? There it goes. So, looking at a protein, there's like the structure, it's the sequence itself. Those are the amino acids that build up a protein. And then it's easy to stop right there. It's easy to think that's all proteins are, which are the amino acids, but they really have different, like, they have secondary structures, they have tertiary structures, they have quaternary structures. And all of these are parts of the protein you have to consider when it comes to drug, like, development. But it's very easy to just get caught up in here, like just thinking about this protein structure itself. Ever since I heard of proteins randomly misfolding, I've been praying my folding guys know origami. It's you know, I'm sure your guys are origamiing their proteins just fine. I'm sure they're not getting caught up. I just disappeared for a moment, came back to so much. You know, don't worry. There's always, you can, if you're lost, that's okay. I can answer any questions you have, or you can just like, you can sit down and relax and listen on. Or you can watch the VOD. Love protein? I love protein too. A lot of what I know about prions is due to friYAY's video on it. They're so scary. Prions are so scary, but also very fascinating. We learned a lot about prion diseases in my biochemistry class. We read a lot about you know, it's Kuru disease. Is that considered? It's a prion disease, right? Yeah. We watched a whole documentary about Kuru, which is a type of neurodegenerative disorder. It's from the people of Papua New Guinea. They had a cultural practice of eating. You know, the people that died, they would eat the whole body, and including the brain. And unfortunately, that meant they were catching something called Kuru, which is a prion disorder. Prion, simplest term, badly folded protein that can cause disease. Yeah. That's the best way to describe it. It's very, very fatal. Very, very bad. There's a lot of different human prion diseases, like Creutzfeldt-Jakob disease is like a common one. Kuru. Bovine spongiform encephalopathy. That's like mad cow. That's like mad cow disease. That's not in humans, so that one's in cow. Don't engage in ritual cannibalism. That should be easier said than done, but you know, sometimes culture be like that. I think the people of Papua New Guinea learned better though. Is there a mad human disease? No. Maybe you just count like No, I don't think so. Brain inflammation, always fun to think about. I don't want my brain to be inflamed. Maybe it's already... I think... What else can we go over when it comes to the alpha? Oh, thank you for the head pat. I get angy sometimes. I get angy too, but I don't think that angy... I don't know if angy is boiling my brain. Yeah. I feel like the basis of this whole lesson when it comes to where cancer research is going is it's all going to be in the computers. It's all going to be in computational modeling, and it's probably all going to be AI. And also, I think the AI is just going to solve everything. Yay, GG, I guess. I always hear I don't know about the job safety of the computational biologists, but when I hear them at work, they don't sound very confident that they will. They don't sound very confident that they will have the same job that they had like in a few years, because I always overhear them going, "Oh man, they're doing it. This ChatGPT is doing my job better than I am." Did we really have a cure to HIV back then? I highly doubt it. I am not like a big believer in like the secrecy aspect. I guess you could say mad human is Creutzfeldt Jacob. I guess that's true. Like, it's pretty related. I am not a big believer in like there's some big conspiracy of like people hiding things. Similar to, okay, here's another thing. If you ever think there's like some weird conspiracy where people are trying not to cure cancer, I want you guys to know that's definitely not true. There's no magical cure to cancer that the big pharma is hiding. Cancer is just very complicated. And there's never going to be a cure to cancer, because cancer is just a bunch of different diseases. Okay, I want you guys to know that. I want you guys to make sure you take that message away at the very least. Two things: cancer is many diseases. There's never going to be like one cure all. And two, the AI and computational modeling, that's where all the future treatments are coming from. Unless we have something that can cure all diseases. I mean, if we can have something that cures all diseases, there's like a lot of other implications that come into that. It's like similar to like, it'd be like, well, how does it cure aging? How fast can cancer cancer really develop in a human body? Well, it depends on what kind of cancer you get. There's a lot of different types of cancers. Some cancers can take a long time to develop, and then other cancers, they can start developing really fast. It's just a matter of different germline, like different risk factors you might have as a patient. Stuff like breast cancer, there's like very aggressive breast cancers where that can develop like in under a year, which is pretty scary. You're gonna have a 300-round therapy to target every receptor. Yeah, like that's the kind of thing I would imagine. If you end up trying to do like a huge treat all cancer, you're just gonna you're throwing a bomb at every tyrosine kinase receptor and like blowing it up, and that's the treatment. Is aging something we want to cure? That's a huge rabbit hole. You know, I had to talk about that in my grad thesis. When I did, like, when you are in a grad program, you have to kind of defend, like, one of the things to get into go from a master's program to the PhD candidacy is you have to, like, defend your project to your council. And they kind of asked me, like, is aging something you want to cure? And then we went into a philosophical debate about that. I think there's aging, and then aging as a disease, which are very different. Can a man really develop breast cancer? Males can develop breast cancer. You have a small amount of breast tissue. Men have a small amount of breast tissue, so it's possible. It's just unlikely. The more, as you can imagine, the more tissue of something you have, the more likely you can develop it. Oh, thank you for checking in, Tomoya. Thank you. Okay. I think we might have covered everything I wanted to cover in my notes. I asked AI what's the hard lump under my triceps and said it might be cancer. So GG's. Oh gosh, GG's. It's over for you. I'm sorry, tax auditor. It's over. I wish I knew more about like the AI cancer detection methods. I've seen some of the people at my work who are the ones diagnosing patients and prescribing treatments. They pull up like some AI tools and look at like different images of patients' tumors, and like it does like a whole bunch of detection methods. It's pretty interesting to see, but I can't speak too much on it because I don't know how it's doing that. A male has 1/800th chance of getting BRCA in their life, which puts them at about 45% just of breast cancer havers. Yeah, BRCA, it's likely it's not going to, it's very unlikely to get breast cancer as a male. But point mutations can happen all the time, whether deleterious or not. There's a lot of different factors. It's hard because, you know, the mutations we get, they're called, you can kind of divide them into two different settings. There's germline mutations, and then there's somatic mutations. And, you know, germline are like in the inherited mutations. Usually, like, you were kind of born with that. While somatic can kind of happen anytime. Like, all of a sudden you decide your DNA repair toolkit's made a mistake, and now you have a very bad mutation occur. And that can happen, and that's not good. How does mutation even happen? You know, that's a good question for next week. Next week, I'm going to be answering any cancer question. We'll add that to my list. How about that? And I can explain all about how does mutation even happen. It can be for no reason, but it can also be for environmental reasons. I'll get into it more next week. I'm going to add that to my list. I once had a hackathon held by a company that the winners were their employees or companies saying they could detect cancer with a selfie. I've heard a lot of stuff like that. Are you American? I am American. American microbe. What time do you stream? I stream 7 p.m. EDT, so like an hour, usually an hour back from here. Whatever time it is for you, I streamed like an hour ago. Are there any bacterial infections that increase our chances of developing cancer? I wanted to talk more about that in next week's stream, Possum, if that's okay. But there are, in fact, bacterial infections that increase cancer development or risk. Next week is more going to be just a bunch of random questions that I've like a compilation, tying everything together, etc., and all that. And then I can make the big long video of all the science streams that we had this month on cancer. This sounds fun. That sounds fun, right? Yay! Okay, I think I'm good now. I feel like I've yapped a lot, and we went off topic a lot. Thank you guys for hanging out with me. I appreciate it. And I will see you guys. I have a stream tomorrow. Oh, thank you for checking in, Tax. I have a stream tomorrow. It's not sciencey. Of course, you can ask me sciencey questions. Oh, thank you for the follow, Tax. Yes, stream is ending. I have a stream tomorrow, and I'll just be drawing. If you want to hang out and watch me draw and yap with me, I will enjoy your company. If not, that's okay too. Okay, I will see you next time. Twitch algorithm cooked with that. Thank you. Well, I'm glad you enjoyed your time. Bye, 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 bye. Bye, bye.